In this section, we're going to look at how we can actually make a solution. So the actual dissolving process or dissolution process. So first thing, you already know this. If I get a solid chemical and I want to dissolve it, stir it up, mix it, you're taking sugar, you want to make some Kool-Aid or something like that. What are some things you got to do? Number one, you probably don't want big chunks of Kool-Aid because big chunks, what do you got to, don't dissolve very easily. So let's talk about big chunks. If you had big chunks, what's the first thing that you do? You break them apart. By breaking apart, what are you doing? You're increasing the surface area. You got this big chunk, this big cube. Doesn't have very much surface area. But if you cut it and fracture it and pulverize it, guess what? You've increased the surface area because you've exposed a lot more surface to the substance. So it dissolves more. Agitating. Well, agitating is just a simple word for stirring. So I guess stir it. You stir it, it'll dissolve faster. And then the last one, and this is true for most substances, you increase the temperature, more of the chemical will dissolve. Now, actually, it's not true in every chemical, but it is true in most chemicals. So 3 things to make something dissolve faster. Okay, pretty basic. Nothing there that probably didn't know already. Moving on to some stuff that probably don't know as much as. Well, on page 410, they have this chart. It's called the solubility of solutes chart. And what this shows us, this tells us how much will dissolve per, in this case, 100 grams of water. And you have various temperatures. And that's how every chart is going to be. How much of the chemical will dissolve? But you got to quantify it. How much will dissolve if an amount of water, but also a certain temperature for this to be true. Now we're talking about 3 other terms here. We have the terms saturated, unsaturated, and supersaturated. The term saturated simply means under a specific set of conditions. So again, certain pressure, volume, temperature, all things being equal. It is the maximum amount of chemical that can dissolve under those conditions. So on the chart on page 410, those are the saturated values. Those are the maximum amounts that can dissolve. For example, you see sodium chloride at 20 degrees Celsius, 35.9 grams. That's its saturation point, the maximum amount. Now, if something's unsaturated, we're less than the maximum amount. So it's under saturated. That's possible. Sure, 35.9 can dissolve, but if I only put 5 in, I'm still under the max. I'm still under the saturation point. Okay. Now, supersaturated is kind of interesting because supersaturated, it's very difficult, number one, to do. So it takes some special conditions and things like that, and it's not very stable. But here's what supersaturated means is we actually are able to dissolve, and this is the key phrase, dissolve more than what the chart says it should dissolve. So if we were to take 38 grams of salt and stir it and heat it and kind of do all those things under special conditions and setup, we might be able to make it maintain that amount that's being dissolved. Now, salt's actually maybe not a great example because if you look on chart on 410, the only way you can get up to 38 grams is if you heat the water all the way up to 80 degrees Celsius. So what we could do is if we're talking salt, you could take 38 grams, heat it to 80 degrees Celsius, and slowly, okay, slow and carefully, lower it back down to 20 degrees. And if 38 grams stays dissolved, we now have a supersaturated solution. But if we cool it back down and it recrystallizes, we no longer have a supersaturated solution. So we could be here 80 degrees Celsius, we get 38 grams, we're good. We come over here, we cool it back down to 20 degrees, and if we still have 38 grams, then we are super. But if at 20 degrees it's only 35 grams and there's 3 grams sitting at the bottom, this is not supersaturated. This is now saturated. I should say 35.9 to be specific. So, difference between saturated, supersaturated, and unsaturated. Now, you've heard those terms before. The difference between saturated, unsaturated, and supersaturated, you've heard it in terms of fats and oils. So just as a quick comparison here, if you have something saturated, a saturated fat, it is full of single bonds. So saturated fats are these big structures of carbons and hydrogens. So imagine a big Lewis structure. All these single bonds, hydrogens bonded to carbon. Unsaturated fats are not full of single bonds. Some have a carbon-carbon double bond. Now, there are polyunsaturated and there are monounsaturated fats. So, what's the big deal? Which ones are the fats that are more or less healthy? It is the saturated fats. Why is that? It's easier to break single bonds, are easier to break, or let's say this, easier to digest. Therefore, if you eat a lot of saturated fat, that's not good because your body can easily digest it, break it down, and store it. What's more healthy is to eat polyunsaturated fats because it's even more difficult to dissolve and digest those fats. Okay, so just simple little comparison there between fats and saturated fats and what we're talking here in solubility. All right, next thing, just two other terms here, miscible and immiscible. Just another way to say soluble and insoluble. These terms tend to get used with liquids. Gasoline and water are immiscible. Rubbing alcohol and water are semi-miscible. Okay, they do mix. All right, so just a couple little terms there, nothing too special. Now, as we kind of work through this, we can also talk about gases, and gases is kind of interesting because with gases, there is some solubility there when we're talking about their interaction. The thing we've got to think about is the kinetic energy of gases. So here's what we're going to do. Let's first talk about gases and the effect temperature has on it. If I want to have two gases mix and I increase the heat, I'm actually not helping myself because here's what happens. If I increase the temperature goes up, the kinetic energy goes up. What happens? The gas molecules move more and they are not going to stay mixed. Okay? So the more energy the gas molecules have, the more they're going to separate or spread out. Right? So as temperature increases, the solubility of a gas actually decreases. As you decrease temperature, solubility goes up. They're inversely proportional. Example is club soda, and we'll see that in class where club soda is basically carbonated water, and it's interesting what it does. Now, page 414, if you look, here's a graph of solubilities, and on the top, you see different gases. As the temperature goes up, how much oxygen would stay dissolved in the water goes down. The hotter the temperature, the more kinetic energy, the less it stays mixed. Very different from solids. Okay? Very different from solids. Most of them are directly proportional. Okay. Also on 414, you see the big graph. So of dealing with the solids. These are important graphs and charts to be able to read. You don't memorize them. You just have to be able to read them, interpret them. And that's it. And we'll do some examples in class and kind of talk about some of that stuff. All right. So here's a graph. You just got to read the lines. So I'm trying to find lithium chloride, and I want to know how much will dissolve at 30 degrees Celsius. Right there it is, about 85 degrees. Interpret the graph, figure out the answers. Pretty straightforward. All right, last thing we're going to talk about is when things dissolve, they actually can either release energy or absorb energy. Things get hot when we dissolve them. Some things get cold when we dissolve them. Two great examples. Number one, instant ice packs. You got a solid, you got a liquid, you crush it up, you mix it. All of a sudden it gets cold. Well, you shake it up, it dissolves that solid inside, and it gets cold. That's an endothermic reaction. When that dissolves, it is absorbing energy in the surroundings. They also used to have the old hot packs. Okay, they're not as common as anymore, but you would actually boil them, and it would dissolve, and then you would snap the little metal tab inside. Next thing you know, it would crystallize. Well, that's kind of the reverse effect. When it recrystallizes, it is exothermic, but you have to boil it to dissolve it. So that example would be an endothermic reaction to get it to dissolve also, because you're forcing it to. Here's the key. How can we feel hot or cold? If you look on that chart, it's got to be plus or minus 30 kilojoules. So when you're looking on page 416, if any number is inside of that range, we probably can't feel it. The two easiest examples to look at are sodium hydroxide, when we dissolve that in water, and ammonium nitrate. Sodium hydroxide, when it dissolves, gets very hot, okay, very exothermic. The value for that is minus 44.51 kilojoules. And that's the other thing. It is going to be negative because negative means release. Okay? And then ammonium nitrate, as you can see in ammonium nitrate, it is positive 25. So it's kind of right on that verge of that 25 to 30. Sometimes we can feel it, sometimes we can't. All right? So there's how now we're talking about the solubility process, how it dissolves, what happens when it dissolves, and all the things related to that. What we'll be doing in the last section is, now that we've got things dissolved, we're going to try and calculate how much is dissolved, and how do we record that, and how do we represent that value.